This is a video about debugging and setting up the QCX 5-watt CW transceiver. In particular, I'm going to be using this very low-cost oscilloscope. These are available very inexpensively. So first, let's have a look at the oscilloscope. This is the DSO 150 oscilloscope. I got it from AliExpress. It's available from a number of vendors. I actually paid less than $20 for this oscilloscope. Of course, it doesn't have the features that you'd expect on a expensive proper oscilloscope, but nevertheless it's very useful, and I'm going to show you how to debug the QCX audio sections with this. The oscilloscope has 4 buttons on it and a rotary encoder adjustment. When you power it up, it needs a 9-volt DC supply, and as I power it up, you can see here it boots up and very quickly shows you the oscilloscope screen. This comes in 2 versions. One of the versions has this crocodile clips. This is not the version I would recommend. I'd recommend the version with the proper oscilloscope probe, which only adds a few dollars to the price. Over here is where we plug in the DC power, and there's an on-off switch, and on the top side there's a BNC switch, a tag for testing, which generates a 1 kHz square wave, and there's a switch to couple the probe to AC, DC or GND. Here it is with the probe clipped on to the test signal, and you can see the frequency display up in the top left hand corner, very close to 1 kHz. It also shows measurements of the cycle time in milliseconds and the pulse width and the duty cycle. On the right hand side, it's measuring the voltages, minimum, maximum and the average voltage, and the peak to peak voltage and the RMS voltage. These are all very useful when it comes to debugging. The oscilloscope bandwidth is only 200 kHz, so it's obviously nothing like as useful as a real desktop oscilloscope, but then again, nothing like the cost either. The oscilloscope comes with an instruction booklet. It's really just 2 A4 color printed pieces of paper. Most of the pages concern construction of the kit, because it also comes in an unassembled form. I actually built the assembled form. I think it's almost the same price anyway. And the actual directions on how to use it are about half a page here at the back. So it doesn't have very much documentation. On the other hand, it doesn't actually need very much documentation. You can see here the if you're used to a normal scope, or if you even look at the tutorial on how to use a normal scope, this is very similar. For example, here I press the voltage per division, and then I can just turn the rotary encoder to choose the number of volts per division. Similarly, I can select time per division here, and I can expand that time axis. And the trigger point, you can have an automatic trigger, or you can set the level, in which case this small triangle on the right hand side can be adjusted by the rotary encoder. So you can very easily find your way around this scope without really needing to refer to the instruction manual at all. It also has a hold feature here if you want to pause the display and take some readings off it. So it's a very nice little unit for $20 really. Now onto the QCX transceiver. A very important thing here is to keep a dummy load connected during the alignment and testing and debugging. This is the QRP Labs 20-watt dummy load. Connecting the dummy load will protect you from transmitting into an open load and damaging the power amplifier transistors. It also provides a better match to the filter, so that your bandpass filter adjustment and other adjustments are more accurate. When you first apply power to the radio, I would recommend using a current limited supply if possible. In case there are any shorts, at least you won't be blowing anything up. So when you power up, you'll initially see a splash screen on the display, but it will look horrible, rather like this. This is not a problem, this is just that you need to adjust the contrast. So it's the trimming up here on the top left, and you typically will have to turn it until the display looks nice, like that. Now there's a lot of people who have emailed and said that they've selected the wrong band, or it shows the wrong band, and for example perhaps they bought a 40-meter version of the radio, what you're supposed to do is select the band on startup by pressing the left button here, turn the rotary encoder to get the band that you want, and then press the left button like that, and then it will show you 14-meter frequencies. But supposing, as in this case, this is actually a 40-meter radio and you've selected the 20-meter version by mistake, go into the menu system by giving a long press to the left button, go up to the other menu and find factory reset option and select here, change that to 17. That just is a way of confirming that you really want to do a factory reset. Now when it does the factory reset, it restores all the contents to default and allows you to select the band again. So this is very important. I do not recommend manually setting the frequencies or just turning the rotary encoder a lot till you reach the frequency that you want, because you won't get the desired results. The quadrature local oscillator generator doesn't work that way. Now you've got this far and you can see information on the display. If you do not get any information on the display, then you need to check areas around the microcontroller. Have you put the microcontroller in properly, in the correct orientation? Do you have any pins which are bent over and not properly in their sockets? If you've got a very early revision of the board, have you carried out the unreliable power startup modification? That's required on the first batch of boards. All of these things, you really have to get the processor operational and something shown on the display like this first before going any further. After checking that you have information on the display, the next thing to do is check the RF power output. Here I'm going to plug on a small one of these DuPont cables. It needs to go on the 1x3 header here on the left of the board, in the central one of those connections. That's the connection for the RF power meter. While we're on this topic, that header, that 1x3 header, is also very close to the 2x3 in-circuit programming header here. You need to make sure you don't slip any wires across, because there is 12 volts on the top of these pins here, and you will fry something in the processor if you do that. That's happened quite a large number of times. Another thing that's commonly misunderstood is the display of the battery icon. It's not an automatic process. You need to actually jumper the bottom of these 3 pins with the top of the 3 pins. So you're connecting the DVM input here at the bottom to the 12 volt side at the top of the header. So once you've connected the DuPont cable or some other cable from the middle one of those pins, the best way to detect the RF power output is to go into the test equipment menu by pressing the left button here, a long press, and then go to menu 9, test equipment, and go to the RF power setting in menu 9.2. So right up here, right next to the top right corner of the board, there is a pad where I can connect very near to the RF output, and that will allow me to measure off RF power. Now I'm going to press the key here, and you'll see that I'm measuring 4.3 watts of output according to the RF power meter. Again, when you do that, make sure that you have the dummy load plugged in. So if you don't see any power here, the thing to check is, of course, the first thing to check is the enamels on these wires of the low pass filter. This is a very common mistake. Hasn't had the enamel scraped off or burned off before soldering, and this is a very important thing, very common mistake. So you can make sure that, as per the manual instructions, actually use a DVM to measure for continuity from one end of the low pass filter to the other end of the low pass filter. It's very important. Same applies to the windings of the T1 transformer here. They all have to be correct, otherwise the receiver is not going to work. By the way, you can pull the LCD module off, as I just did, and the radio will carry on functioning completely normally. It talks at the LCD module, it doesn't seek any response from it. But if you plug back on the LCD module when the unit is operational, you'll just see blocks like this, because it hasn't gone through the initialization sequence. So to get back a proper display, you need to cycle the power again. Now we'll come to looking at the receiver section. The receiver section is where most problems usually arise and is also the hardest part to solve. But if you use a methodical method, you can usually find the problem. An oscilloscope is very useful in doing this. What I've done here is I'm using my standard oscilloscope probe. This is from my normal oscilloscope, and I've clipped the negative wire onto the tab of the 7805 regulator up here at the top left of the board. Make sure that you put the probe in its ×1 setting, if it has one, because this oscilloscope doesn't know about ×10 probes, ×1 probes. It is a very simple one after all. Now the strategy here is going to be to refer to the circuit diagram and trace the signal through from the input, from the RF input, all the way through to the audio output here at the headphones on the left. So before we do any of that, the first thing to do is use a simple ordinary DVM, digital voltmeter, to check the supply voltage across each of the op amps. You do this by putting the negative probe on pin 4 and the positive probe on pin 12, and you should see something like this. I'm using a 12 volt supply, and so you should see a little bit less than 12 volts because of the reverse protection diode, which drops about 0.3 volts. The reason for checking this is that in all my fault finding I have seen quite a significant number of occasions where the ground pin of the op amp, which is pin 4, has not been soldered properly to the ground plane. The reason for this is that the ground plane dissipates quite a lot of heat, and so therefore it can make soldering a bit difficult. And so you need to put a bit more heat when you solder the ground pins, otherwise you may not get a proper connection. So there we have IC5, pin 4 and pin 8. So if you go through from pin IC5, 6, 7, 8, 9 and 10 here, if at some point you find that you don't see the proper supply voltage, then you can go back and investigate there whether you've got a dry joint. Now you could also make those DC voltage checking measurements with the oscilloscope. It's very useful for making that kind of measurement. I was just showing the DVM in case you don't have an oscilloscope. So for example, here I'm touching the probe on pin 8 of IC5, and you'll see that the beam totally went off the top here. The first way to resolve that is turn down, move the Y shift here. So you see this, when I press this button on the left, it changes between the volts per division and highlighting this blue arrow on the left. I can then adjust that with the rotary encoder on the scope to bring it down to 0. Now I will touch the volts per division button and change that to 2 volts per division. And now when I put this probe again on pin 8, you'll see the line that comes up here, and you can see up in the top right hand corner a measurement of the voltage maximum here. 11.84 shows you the RMS and the minimum, the average, and all of those are roughly the same as what we saw on the DVM and what we expect to see. Now assuming you've got the proper supply voltage on all the op amps, the next thing to do is put the unit into the alignment mode and go for the menu 8.7 bandpass filter adjustment. Now you should hear a horrible loud tone. Make sure this isn't in your ears at the time you do it. I'm just going to turn down the volume to turn that off, and now you'll be able to adjust the trimmer potentiometer here, and you'll be able to find a peak. So you can see that as I turn it, you can find a peak, and you should expect to see the peak at somewhere around the middle of the travel of the trimmer capacitor here. If it's all the way at one end, so the vanes are all the way closed, or if it's all the way open, then you have a problem and you need to either remove or add some turns to the main winding of T1 as described in the manual. But if you can find a nice peak and the peak is somewhere around the middle, then that's a good indication that the first part of the receiver and the audio chain is working. You can then proceed to looking at the IQ balance, and the low and high audio phase adjustments, what you see here will be a very small number at the top right of the display. You need to actually increase the volume to get something reasonable to work from. And then you can adjust these 3 trimmer potentiometers as it says in the manual. You need to go backwards and forwards a bit between these two, which is the menu settings 8.9 and 8.10, as they do affect each other. And so you'll quite often find that as you trim one and then go back to the next, you'll find that you end up chasing the adjustments seem to chase each other. Each time you change one, you need to change the other more, and then you go back and you have to change this one more, and so on. But you do find a point where they both minimize the display, and at that point that's where your adjustment is optimal. And then finally go back to the IQ balance menu 8.8 and make a final adjustment to minimize the IQ balance, because again it does affect that as well. So now the question is, what happens if you do not see the expected results, and this is where you must have a fault somewhere and you need to start debugging. Now you can even do a fair amount of this with just the DVM. So this unit does work as it should. It's a properly working QCX radio. So I'm just going to be showing you really what happens, or what you should expect to see if everything is working properly. And what you can do with reference to the circuit diagram, you will find that you should have 2.5 volts of DC bias on pins 1 of the op amps. So here's IC5 pin 1, and you can see it's roughly 2.5 volts, a little more, that doesn't matter. Same on pin 7, and so each of pin 7 and pin 1 on IC5, IC6 and IC7, as well as on IC8 and IC9B, all of these should be approximately 2.5 volts. 2.6, 2.7, 2.4 doesn't matter, but approximately in that area. On IC9A, you expect to see at pin 1 a DC voltage when measured of about 5 volts. So here I'm going to measure that, and you can see, there we go, 5 volts. Now on both pin 1 and pin 7 of IC10, which is the final audio op amp here up in the top left, you expect to see about half the supply voltage. So here you can see 6 volts. And this is a very, very good indication, okay, because if the DC bias voltage is correct on all the pins, it generally means that everything is in good shape. And what you can do is you can go across from IC5, 6, 7, 8, 9, 10, and the signal does flow through in this direction. And at some point, if you have a problem, you will find that you don't have the expected DC bias voltages. So what kind of problems could you have? You could find that when you increase the volume here, you don't hear any tone at all. That would indicate the problem in the final audio stages. If you see something on the display here but you don't hear anything, it means the signal has got up to a certain point in the audio chain but not to the final output. Or you could find that when you're doing the phasing adjustments and the IQ balance adjustments, no matter how much you turn the trimmers, you can't find any minimum, or perhaps the signal doesn't change at all and it's still just as loud as the main signal in the bandpass filter peaking menu. What this means is that one of the paths, one of the I path or the Q paths, has a fault in it. These are IC5A, 7 and IC6. These are the I and Q paths, and if one of them doesn't have the correct behavior, then you'll get no unwanted sideband cancellation and you will not be able to find a minimum. Now I've put the oscilloscope back in the 1 volt per division mode here and looking at pin 7 of IC5, and what you can see here is a 700 Hz sine wave superimposed on a DC bias of about 2.5 volts. So you can see the DC bias measured up here, the average voltage 2.51. This is slightly different to what the DVM measured, because the DVM wasn't necessarily measuring the average, it was messed up by the AC frequency on top of it as well. Now if I adjust the trigger, if I press the trigger button to highlight that blue marker there on the right hand side of the screen, I can just about scale it to be able to cause it to trigger on that 700 Hz audio signal, and then you can see again 700 Hz up here in the measurement on the top. Now this is the very entry point into the signal chain, and if you don't see a 700 Hz signal here, then you need to look at transformer T1 and whether or not you've soldered the endings correctly, whether you've got the wires in the correct holes, and you need to look at everything around that area first. So this is one of the channels, the Q channel, which is pin 7 IC5B. Now if I go and have a look at pin 1, I will see a very similar signal, hopefully. Slightly different DC bias, that's nothing to worry about, and I can just turn the rotary encoder to be able to lock that one on, and you can see again now it's measuring the duty cycle and the frequency at the top there. Now if I go to the next one, IC6, again I see a very similar thing, about 2.5 volts of bias plus a 700 Hz signal. I expect to see the same on IC6 pin 1 and on IC7 pin 7, as well as on IC7 pin 1. So I expect on all of these output pins of the op amps, pin 1 and 7, for IC5, 6 and 7, I expect to see the same thing, which is a 2.5 volt DC bias with a 700 Hz signal superimposed on top. Now I come to look at IC8, and I am touching the probe here on IC8 pin 7, which is the first op amp in the CW filter. So this is a 200 Hz bandwidth filter centered on 700 Hz, and you can see that it also provides some gain. We've already had some gain provided by the fact that we're adding the I and Q channel, and they're reinforcing each other, and each of the stages of the CW filter provides a bit of gain as well. So starting with IC8 pin 7, as we go through we expect the signal to get larger and larger. Here we are on IC8 pin 1, and you can see the signal has become larger again, and at IC9 pin 7, which is next in the chain, you'll see we have about 1.7 volts peak to peak, still superimposed on the 2.5 volts average. However, now when we come to IC9A, you will find that it has stepped up to being on a 5 volt average. Again, the signal has got quite a bit bigger, but now it's got a 5 volt DC bias. Now I can go back to the trigger. I can select this blue marker here on the right by pressing the trigger button, and then turn the rotary encoder up until it's inside that signal, and we'll start triggering on it. And you can see again the 700 Hz measurement and a much larger peak to peak voltage of 4 volts peak to peak. Now when I come on to pin 10, sorry, IC10 pin 7, you'll see here I see nothing at all. Why? Because this is after the audio gain control. Now as I adjust the audio gain control, you'll see that I can adjust the amplitude of the sine wave at that point, and now it's on a 6 volt DC bias. As I explained before, you can refer to the circuit diagram and you will see why these biases come in at these values. So what you should see here is a sine wave whose amplitude you can change by turning the gain control potentiometer. I'm going to switch the scope at this point to 2 volts per division, just to get a better view of it. So here we have 7 volts peak to peak, and by adjusting the gain I can take it all the way down to 0, or I can take it up so high that it clips the top and bottom of the sine wave, turning into a square wave with about 10 volts peak to peak amplitude. I should say at this point that I had taken out the earphones. If you put in the earphones you get a much more horrible waveform because of overloading the output of the op amp, which I'll show you in a moment. So now to turn that down, to turn the audio gain to some small level, say smaller level, that rather than peaking 7 volts peak to peak. Now if I look at pin 1 of IC10, I should see exactly the same voltage, a very similar looking signal, because the final stage of IC10 is just a unity gain buffer. Now here I am with the earphones plugged in. I'm using an old pair of mobile phone earphones from an old BlackBerry mobile. Now I have the gain setting very low, but you'll see what happens as I turn it up. The signal starts to get very, very distorted, and if I turn it to maximum, you're seriously starting to overload the op-amp output, so it gets extremely distorted. By this time you'd be completely deaf, so it's not really a situation you ever encounter in practice on the air. You'll be within the linear behavior of the op-amp when you're using the radio in practice, otherwise you'll be deafening yourself. The use of an op-amp for the final audio amp stage was just an economy to try to streamline the design and the costs of the project. Now, if you don't have a DVM or an oscilloscope, you can still do a fair amount of debugging by using the QCX's built-in DVM. To access this, you connect a wire to the bottom of the 1x3 pin header here on the left-hand side of the board. Again, make sure not to touch anything against the 2x3 program header. That's the cause of quite a few problems. Now, go into the test equipment menu, menu 9 and 9.1, the DVM. Now you can go to look at pin 8 of IC5, for example, and you can see 11.63 volts, the same as what we measured on the DVM earlier. This is not such a good method because we can't measure the ground voltage. If I put my pin on pin 4 of IC5, it will measure 0, exactly the same as if I hold it in the air here measuring nothing. So, but it still can be very useful for measuring the DC bias. Here I'm looking at pin 7 of IC5. You can see 2.54 volts, exactly as we expect. As I go across and now look at IC 9B, I still see 2.54. At 9A, I see nearly 5 volts, exactly as I said. And on IC10 pin 7, we expect to see a 6 volt bias, which is half of the supply voltage. So you can use the DVM to check those bias voltages, and again, if you find any problems anywhere, you can go and investigate that in more detail. So to recap, debugging the receiver chain, the signal flows from right to left across the board, and if you look at the circuit diagram, it flows from left to right across the circuit diagram. The technique is to put the radio into the bandpass filter alignment mode, which injects a signal into the front end of the radio, a loud signal, in fact, loud enough that you can trace through all of the audio stages, and at some point you will find somewhere where the DC bias is wrong, or where the sine wave signal that you're expecting just disappears or is very distorted. And once you've found that point, you know exactly which op-amp has the fault. You can then look at the components feeding that op-amp from the previous stages, look at the feedback elements across that op-amp, the resistors and capacitors, check the resistor and capacitor values, check that the soldering is all correct, check there are no solder bridges. What we've seen a number of times is very, very tiny cracks in PCB traces which can hardly be seen. So check the PCB traces. If you think that two components ought to be connected by a trace, check those traces with the DVM in resistance mode, check for a continuity. That's an easy way, but an awful lot of problems can be solved visually. You may have a component in the wrong place, you may have installed an incorrect value component, or you may have a soldering problem such as a dry joint, a solder bridge, a short circuit, or a broken trace. All of these problems can easily be resolved once you find them. Finding them is the trick, and the trick to this is being very methodical as you move through the signal chain. Nearly always the problems are due to soldering or incorrect component placement. It's very rare that there's an actual broken component. This is a common mistake. People always assume that the components are broken rather than that they themselves have made a mistake. It's I guess a way of finding somebody else to blame, but it won't help you to fix the radio. Often, and I've done it myself many times, replace a component and find there was nothing wrong with the original component. The problem is a problem with the soldering. As for this oscilloscope, well, it's a really nice thing to play with. It's really useful as well. I really enjoyed playing with it. I found it very intuitive, easy to use. It's not going to do for looking at RF because the bandwidth is 200 kilohertz. It's just simply not high enough bandwidth to observe RF with. But for audio purposes, this is a really nice tool. It's very inexpensive, but it certainly is not just a toy. It's really a lot of fun to use and quite intuitive. For the price, pretty unbeatable. And if you don't have an oscilloscope and you want to get into using an oscilloscope or learn more about them, then this is quite a nice introduction as well as a useful aid to have around the shack. I didn't really need it. I have a full-size oscilloscope which I use every day, but I bought this one just to see what could be done and had the idea that it would be quite nice for debugging QCXs with on a budget. And now the QCX is all nicely working. We can plug in the shack audio amplifier and turn on the power. Let's change the dummy load over for the antenna coax. Let's see on the QRP frequencies. And now the QCX is all nicely working. We can plug in the shack audio amplifier and turn on the power. Let's change the dummy load over for the antenna coax. Let's see on the QRP frequencies. So I hope you enjoyed the video explaining how to debug QCX problems with very simple equipment, and I hope you enjoyed the demonstration QSO with Nick LZ1NG. This is Hans, Golf 0 Uniform Papa Lima in QRP Labs headquarters. Thank you very much for watching. Bye bye for now.